the last day and last show of PyCon India, and I think like very few people are interested in SciPy. So, anyways, yep, let's begin the talk. So, yeah, I am Gagandeep Singh, and I work at Quantsite Labs as a software engineer, and I work on like SciPy, NumPy, like I contribute to those libraries. And so, yeah, today I will be talking about some of the significant enhancements I made in SciPy over the last 3 years while working at Quantsite Labs. So, yeah, let's begin. First, let's see what is SciPy. So, SciPy is basically like a library for everything mathematical and numerical computing, like optimization, integration, eigenvalue problems, algebraic equations, like everything mathematical and statistical, and like it's all about numerical computing, and it's distributed under like BSD license, so it's open source, free to use. Yep, and it's like completely like publicly maintained on GitHub by like a variety of contributors from diverse communities. So yeah, what I worked on Quantsite Labs, like what I worked on at Quantsite Labs to enhance SciPy. So I worked on three things. Like the first one is direct algorithm, which is added to SciPy.optimize, and then DNX algorithm, which is like a maximum flow, like maximum network flow algorithm. And the last one is like adding install tags for test to reduce the wheel size of SciPy. So let's like see what are the expected takeaways for the very few listeners here. So like if you are interested in contributing to large projects, so you will get to know like through my experience what all it takes, and like users of SciPy, if any, will learn about new functionalities added to SciPy over the last 3 years, and like folks interested in algorithms will get under the hood insights. So the first one is direct algorithm. So direct means dividing rectangles. So as you can see in the pic, like there are so many rectangles and each one is divided into subdomains. So that's what it is about, like dividing subdomains and like narrowing down the search space. So the context is like real world optimization problems like are like black boxes. You don't know the function definition. Like real life is not like fx is equal to like x square and stuff like that. So you don't know what that function definition is. You can just only pass the input and get the output, like sample the function. So direct algorithm is specifically for optimizing such kinds of functions. And yeah, so that's what it is about. And so like if you know like the the basic method to compute the minimum of a function or maximum of a function is simply just calculate the gradient, set it to 0, and that's it. Like, and you get the global minimum or global maximum. But for that, you need to know the function definition, and like it should be Lipschitz continuous. So this is the constraint which every Lipschitz continuous function satisfies. Like you should, there must exist a constant k which should satisfy this equation, like inequality, and this inequality turns out to be like converts into two inequalities further, and there is this Schubert algorithm which like divides the full domain like xl to xu into subdomains further, and for that you should need to know the value of k or should be able to estimate the value of k. But if you don't know the function definition at all, or you don't have much opportunity to sample the function to estimate k, then like this algorithm will fail. So yeah, and direct algorithm, what it does, it's very simple. What it does, it just takes the samples at midpoint. So instead of like, you know, like sampling, instead of like dividing the subdomain based on the value of k, it just divides by using the midpoints. So that's the heuristic which it follows, and like everything works out fine. So yeah. So the process of addition of direct algorithm to SciPy is like we rendered it from NLOPT. So this is something like which one of our fellow like open source contributors implemented, like the library NLOPT, and we just rendered it into SciPy. And yeah, so the original implementation was in Fortran. So like the guy ported it into C language, and like we rendered it into SciPy. So that's how the structure file structure looks like for the direct algorithm. So here are the files, like all the C and C header files and C implementation files, and all this is connected to scipy.optimize like API via Python C API. That's like very standard procedure. And like benchmarking direct algorithm, so yeah, so you can see like it performs fairly well. Like it solves 156 out of 195 problems in SciPy's benchmarking suite, like which is like in my opinion, excellent because like it treats the function as a black box, and like without knowing anything about the function, if it's able to solve like these like this very high percentage of optimization problems, then like I think it's excellent. So yeah, and it's available in the latest release of SciPy on PyPy and Conda ports. So yeah, you can like download it and use it. So yeah. Now moving on to the next addition, which is like Denix algorithm. So yeah, so what is Denix algorithm? It's like computing maximum flow in a flow network, and like it's like polynomial in the number of vertices, and like as opposed to its like Edmonds-Karp algorithm, which is like polynomial in the number of edges. So yeah, so the basic template followed by like every maximum flow algorithm is like you set all the flows to zero for all the edges, and then these two steps are like variable in each of the algorithm, like constructing the like finding like a valid flow and then updating the existing flow and then just returning it. So this loop is like sort of a template, and the specific to Denix algorithm is these two steps. So it computes a layer graph by doing a BFS from source, and then like it calls DFS and then to find a flow, and then the flow is updated. So this loop is repeated until like there is a short until like a path exists from source to sink. So that's how it works. And the addition of Denix algorithm in SciPy like was performed in two steps. The first one was like adding the recursive implementation. So you saw here, like this DFS step is recursive. So like first this recursive implementation was added, and then the shift to iterative implementation happened. So yeah, and then some improvements to pre-processing step of the algorithm were made, and then like the whole algorithm is implemented in Cython. So you can see the screenshot here. So that's how it is. Like the original implementation which I added was like recursive. So you can see the function called to augment paths, and this was like transformed to iterative by using the stack logic. So what the compiler does for you is like internally also each recursion is implemented something like adding calls on top of each other on a stack. So I did it manually and like implemented the like whole algorithm iteratively. So yeah, and the benchmarking results look something like this. Like the SciPy's Denic algorithm performs like fairly well as compared to Google OR tools, and like it beats like Google OR tools as the density increases. Like as you increase it to like a fully connected graph, so it starts to beat like the Google OR tools. Like Google OR tools also performs the like same like the motivation of Google OR tools is also the same, like computing maximum flow. Like the full form is Google Operation Research Tools. So yeah, and the next thing is reducing wheel size of SciPy. So first, like why the reduction is necessary? The reduction is necessary because the number of downloads which SciPy receives is like in millions each month. So even if a small reduction happens, then you save a lot of internet bandwidth. So yeah, so like when we like drop the test suits from the distributed wheel size, a 4.6 MB, which is like 18.32% drop in the distributed wheel size, and like that's excellent because like it saves like petabytes of bandwidth usage, and even the like the downloaded wheel size is also low, so the memory consumed on the user's system is also low and lesser environmental costs. So how we made it happen? So it's very simple. So SymPy uses Meson as its build system, and like Meson provides a facility to like mark which submodules you want to install. So we just mark install tags, like the install tags for tests, as like only install it when the certain like particular tags are present, and like that's how like tests get excluded while building the wheels, and the CI checks the final installation for presence of test files, and like that's it. So yeah, so if you have any questions, then yeah, you can ask.
Gagandeep, that was a quick talk.
Yeah.
Any questions?
So the direct algorithm dividing rectangles, like how many dimensions do you work for? Is it only two dimensions or
No,
more?
it's multi-dimensional. Like it works for any number of dimensions. But yeah, the time complexity increases and the execution time increases with the increase in number of dimensions. So yeah, like it performs fairly badly as compared to the ones which use function definition for computing the like global minimum or global maximum. So yeah, like direct algorithm works fairly well for lower dimension problems like 3, 4 dimensions. But if you increase the dimensions, then I think you should know the function definition for like shouldn't rely on direct algorithm for that.
The second question is, what are your learnings from contributing to SkyPy? Like, is it like easy to do? Is there somebody who decides a roadmap? How do you decide what to contribute? How much time does it take?
Well, I work on full time at SciPy at Quantsite Labs, so yeah, like, and it's fairly like very hard to like contribute these algorithms, even if you are like vendoring it from third party sources and third party fellow open source computers, but still it's very difficult because like connecting it to the SciPy API is tricky because taking the data from the like user's Python input and transforming it and sending it to the library you are using, the third party C implementation or Fortran implementation. So yeah, it's fairly difficult. Like I got like 300 review comments for like direct algorithm. So yeah, and from variety of like people contributing to SciPy.
So, is there like an internal guide to how to contribute, or what are the internal APIs to use?
There is no internal guide, I would say, but yeah, like you should use the existing patterns. So say I added QR decomposition algorithm to NumPy. So like that's a matrix decomposition algorithm. So there are other already present. So what I did was I just followed the pattern for others and added my own implementation, like hooked in my own implementation there. So yeah, follow the existing patterns there, and like yeah.
Thank you. Anyone else? All right, Gagandeep, thank you so much.